So, like I said, the big idea is that we want to learn as much as we can from simple observations. Let me show you a simple observation. Maybe you've seen this video before. I use this to talk and teach about shear thinning, yield stress fluids. I don't need to show you rheometric material functions for you to know something about what's going on. I'll describe some things here. These are two liquids loaded into syringes, a green fluid in the back, clear in the front. It's a little tricky to see. This is water in the front. The green one in the back from this video alone tells you that this is a shear thinning material. You know that it flows because you see it going through the nozzle. You know that it seems to stick around even under gravitational shearing stresses. We don't quantify them here, but you certainly could quantify them and even get a lower bound estimate on what the apparent yield stress is. You could maybe even estimate things like the viscosity from the shearing stress in the syringe. And this is the nature of this protorheology. There's a lot we can learn from simple observations. Speaking of simple observations, this has been a good week for observations. I was a little late joining the conference because I made a promise to my family 7 years ago that I would take them to the total solar eclipse that was coming through the US, and that happened on Monday. So with family and friends, this picture here, that happened. We were lucky, we had clear skies. There's me acting like an idiot pointing up at the sky like nobody knows where the sun is or something. And here's what we saw. I hope you get a chance to see a total eclipse in your lifetime. It's so wonderful. The next one is in northern Spain, 2026. So if you're interested to organize a conference there so I can attend and see the eclipse, I welcome that. So here's what we saw from my camera, just a couple images with the filter on. I think the video maybe, there we go. And of course, this took about an hour and a half to get to totality, which is there. And then it was gone in 3 minutes and 50 seconds for me. But I was able to see this, and if the lighting is right, I don't know, as grand as this is, of course, in person it's better. There's this pink prominence that's at the bottom. Maybe some of you have seen the photos of this. These are really special. This connects to the talk, by the way. This is all about observations. Ooh, we've been eclipsed. Thank you. We'll switch them back on in a moment, I hope. But this was a prominence visible with the naked eye, which is pretty special. You need a total eclipse to be able to see that. It doesn't appear with a partial, even at 99%. And it was the magic of discovery. I had a friend with me who had a telescope set up that could zoom in on that. I don't have his picture, but I have another one that's zoomed in even more. And this is what we saw when we looked through the telescope. It was magical. We had no idea. But you learn a lot by just looking at things. And in fact, the history of solar eclipses and prominences has a nice connection to science. Back in 1860, these were first observed and actually used to quantify and learn about what's going on with the solar atmosphere. As I write here, determine things like altitude, emissivity, and other things for the first time. And this is related to this protorheology paradigm that any observation gives you a chance to infer some sort of quantitative property. And today I'll be talking about rheological properties. Maybe one of you could analyze this rheologically. I bet there's something interesting there. The size of this is like 2 or 3 Earth diameters, so it's quite large scale. Choose your dimensionless numbers correctly so we all understand what you're talking about. But that's the protorheology paradigm. So if we can get the lights back up, or maybe I can, it's the AV. Yeah. But I'll bring us back to that first observation we made together, which was here with these syringes. And I'd already talked about what you might quantitatively pull from this. Let me give you a more specific example, and this is just by chance that what I had put on my slide was at the front of the lecture room, Purell hand sanitizer. And this doesn't happen to have air bubbles, maybe a little bit at the top, and I've seen some great talks about bubbles trapped in elastoviscoplastic fluids. Just a little example of why it might be useful to do this simple quantitative assessment. So when you see this, it has a pump. You can guess that it flows, even if you've never used it before. You see bubbles that are trapped for some long amount of time, suggesting it also has something of a yield stress, a stress below which there's minimal flow. You zoom in and you can get the size of this, and thanks to analysis done by people in this room right now who have solved the forward problem to understand what is the yield stress required to trap a bubble, we can try to do the following. We can try to guess what the yield stress is by just seeing what's the maximum bubble size that's lodged in place. Maybe you've done this before. Before I got into this in the last couple of years, I would do this, but just qualitatively. You know, I'd like stop at this has yield stress and I would move on. And what's been really insightful is to try to quantify things. That's my invitation to all of us here. So let me try to quantify. First, you do it the wrong way, which is to just guess a quick scaling law. Okay, it's something like a density difference that gives me the net buoyant effect times the gravitational force per unit mass times the length scale, and you get something. This is totally wrong, because the fluid mechanics gives you a numerical factor for the dimensionless group, the yield gravity parameter, if you frame it that way, that tells you that you actually need a numerical factor in this framing, something like this. You're off by an order of magnitude from the simple scaling. But like I said, people, I know John's here, I think Imad is here, Ian is here, maybe others, sorry if I haven't seen you. But the number you get is 2.5 pascals. And you can do this before you measure your data. You see on the right, I'm setting up a plot of steady flow data, shear stress versus shear rates. And this is my other invitation to you, to make these estimates even before you see the data. You can anticipate things. Let me show you another rheology gone bad, which this helps actually. You've seen data like the following. It looks like this, these open symbols suggesting a very low yield stress, less than a pascal. That is super small, as we know. And if you just saw that data and you're really in the know, you would say this might be slip, or maybe you'd call it double yielding, and you'd write a paper focused on the double yielding phenomena of hand sanitizer. You'd be wrong, it's actually slip, and many papers have been written about that. You can tell it's maybe slip because kind of this double yielding thing. The Protorheology tells you the yield stress better be larger than this, or it doesn't really make sense. And when you look at the true data, where we correct for slip, we have sandpaper on the plates, we check a couple different gaps, it's actually 5.4. Is this wrong? No, this is just a lower bound estimate of what we expect it to be. As long as it's above that, things are within check. So this is the spirit of Protorheology. What does it give us? It gives us expectations even before we make a measurement. It enables checking bad data, which some of you know I really like to do. And I think it enhances interpretation, as I know many of you do, to just show a picture next to the rheometry that you're showing to give somebody some insight about what the data really means. Here's a quote from a now retired industrial rheologist. I never trust data from a rheometer unless I've also stirred the material, meaning to kind of stir it and kind of get a feel for what it really is. I think Bob is right, and I'm also cynical about the data. Of course, there are many, many ways to stir or play with the material, and so we started thinking about that. Some of these that I'll talk about today are very familiar. You'll see things like the slump test, well analyzed. I hope you see something that you haven't thought about before, and maybe see equations that you haven't encountered before. Here are a few things, and you'll see we can quantitatively extract several things from left to right, maybe a yield stress from a scooping sort of test. A bouncing test actually gives us a good estimate of tan delta. It's not G double prime directly, it's actually the lost tangent. I'll talk more about that later. You can estimate viscosities from a sliding velocity. You can rapidly estimate, I always emphasize estimate, some extensional viscosity by just looking at gravitational time to break. And from die swell, which we know, you can get N1. You can also, with some careful assumptions, get a relaxation time. One thing I'll point out, and you'll see it more later, when you report out the quantity, we've realized it's very important to associate that with a particular forcing strength or even time scale. So this is the idea. I really want to acknowledge many of us already do this. You've heard me say that a lot. The big idea is that we really saw an opportunity to organize what's out there. We kept finding things we were surprised by. I've seen things this week that have been fun and surprising, and so nothing I say will ever be complete, but hopefully instructive and get some lessons learned and some best practices. So this is now published in the Journal of Rheology, thanks to Dimitris for encouraging a creative paper. It's not quite like any other paper you'll see in the Journal of Rheology. Appreciate the forward thinking there to let that happen. Okay, so some definitions and doubt. Because I still carry a little bit of doubt that this can actually be useful, you know? Like rheology maybe started with proto-rheology, but then we rapidly moved on to well-controlled flows, isolating effects. And so this should be a doubt in your mind too. Are we really ready to go back to the complicated stuff? I think the answer is yes. Some definitions. So we call it proto-rheology because this is often the first thing you do. I see the material and I shake it, you know, whatever I do first. That's why we say proto. Your first thing may be different than mine. And anything that's quantitative is always an approximation. There are a few other definitions depending on how you want to use this term. So I especially want to emphasize observing things that are non-ideal, non-trivial velocity fields. There are people in this audience right now that think this way. like inverse problems. What can you learn from a complicated velocity field? I think that's very interesting. The plenary yesterday hinted at non-trivial velocity fields that may be very important for really understanding materials. And more generally, just the general paradigm that it's a chance, any observation is a chance to infer properties. Some comparable terms to keep in mind is the word prototype and proto-human. In both cases, something that comes first, that's not fully formed, but from which maybe there's something to learn or something better can come after. Let's hope so. In the world of rheology, proto-rheology really is the first thing we do. And here's the doubt, like, if you know me, you know that I am so cynical whenever I see rheometry data. How could I ever believe any proto-rheology data? And we certainly value accurate rheometry in controlled settings, so what's going on? And I really think that the prototype idea is the argument to have in mind for why this is valuable. It's rapid, it's fast. We've had a lot of great success doing high throughput testing with things you can look at that are in situ, that are good enough to make a decision and still learn something about the material. Okay, let me show you a few fun examples that many of us are doing this. But as you look through these examples, try to think about what rheological phenomena you're seeing, and none of the examples, very few of them are actually quantitative, just like I used to be. I would stop at the qualitative. The first example I'll give you is Richard Feynman, who did that show up as 1886? I'm going to edit this in real time because that is... In 1986, with the Challenger disaster, Richard Feynman was on the commission, and at a public hearing, he helped to explain to people why the primary reason for that failure, which was that the O-rings couldn't sufficiently recover. Simon would love this. It's a recovery rheology problem, that at cold temperatures, the recovery wasn't fast enough. And I don't know what I've done to ruin the presentation now, but it won't let me change it, so. So I'll ask for your forgiveness. Thank you for that. And he really was doing protorheology. He took an O-ring, same material, he dunked it in ice water, clamped it together, lifted it back up again, and showed that it was very slow to recover back. And just to make the point, of course, that can't be the whole report. We all recognize that. But it's the prototype. It's the way to get the message across, and then you back it up with the details. And I think protorheology serves the same purpose. Some of our favorites include things like the pitch drop experiment. I would call this a protorheology test. We learn a lot from it. A lot of us use this in teaching. And it's been quantitatively analyzed, which is pretty cool. There's a paper in 1984 that analyzed several decades here, pulling out a viscosity that was on the order of 10 to the 8 Pascal seconds. And I really like that next step to say, not only is it just taking a long time to flow, you're not seeing a relaxation time. You're not seeing an elastic modulus, you're seeing a viscosity, and that's what you can pull out from this careful analysis. I don't have time where I would go to the video, but I will point out that if you're really eager to do protorheology right now, you could go to this website and watch the pitch drop experiment live feed. I hope I can be a little more interesting than that, at least over a longer time scale. So here are a few examples. From the most recent Society of Rheology meeting, the first plenary showed protorheology. You see the classic tilted vial test here. Here was another one from Simon's group that I happened to grab, just showing that little picture in the top right that just gives you the sense that this is a yield stress fluid, which is very pedagogical, very nice. This is Krutarth who's giving the talk. Wilson Poon, who gave a plenary, also showed protorheology. Look, it's like the same picture of the Purell hand sanitizer here. He was thinking about the scoop test also. And then I realized a lot of Europeans are doing this, even in Chicago. So here's an example from Aaron Kusa's group. This is a figure from their science paper, which in a high-profile place makes it very nice as an entry point. This is from Jan Vermont's group, showing pictures and videos, again, to kind of give you a feel for things. They weren't quantitatively analyzed. It was a qualitative thing. And really, more Europeans than Americans, I think, ended up using protorheology visually in Chicago. But I've seen it here, too. I just saw a great talk today by Michel Klotz that I show here. Thank you for letting me take the picture and not being distracted during your talk. I didn't tell Michel that I would be using this slide. I hope it's okay. But it was great. And he had a great quote that said, videos are great, and sometimes we want to make a real measurement. And then he went on, which was great. My invitation to Michel and everybody, this video, I love this video. I was pulling out linear information, nonlinear information as he's dipping in and pulling out. There's an opportunity to be quantitative, though, because I think that you see right away maybe what a yield stress is, maybe even see elasticity as this sort of ringing happens, this jello jiggling, just to see if it's consistent. And I think those types of opportunities tend to exist all the time whenever we take a picture to make the quantitative connection. You love photos. One of you gave me this quote. Cornelio Balan gave me this quote. A good photo is more important than a rheometer. And that was not prompted by me giving him the whole talk or anything. He just came up to me and said that when I arrived here the first day. Good photos are good, but videos can be better. Here's a video that Eric First took at a Society of Rheology meeting. I don't know if does the sound come through a little bit? This is the cheese dip. I'm making jokes about dripping on substrate, thinking about Vivek Sharma's work on these things. I'm not sure how much extension we see. We haven't analyzed this, but there's another invitation for anybody else to give some quantitative feel to this. Here's another video. Dimitris isn't here, but I know Gareth is. Gareth kindly sent me this video, and I'm glad the sound is running. I'm going to play this for us all to enjoy. We're having fun at the final talk, I hope. That's kind of the idea.
Okay.
A demonstration of
so we can see the whole action.
Yeah, let me know when you're ready.
I'm
ready. You're ready? Are you recording?
I'm recording.
This is for Randy. We are doing a proto-rheology experiment. I've been informed this has a yield stress that's high enough to hold over Dimitri's. And it has indeed. Yes. Yay! There we go. Okay.
Isn't that great? I'll have a quote from Gareth that's a rough quote, but something since at least 2004 Gareth has put in my mind, which is that a picture is worth 1,000 words and a video is many frames per second. Lots of words coming through. Speaking of moving pictures and videos, maybe some of you know that Leeds historically was one of the starting points for the first ever moving picture, for real. Louis Le Prince is considered the father of cinematography. There's a picture of him. He took this video on the right of traffic and pedestrians crossing Leeds Bridge, which maybe some of you took on the way to the conference dinner. Here's the video. It still exists. I wouldn't call it proto-rheology, but there is movement. and there's a plaque that commemorates this, if you want to check it out. It's on the Leeds Bridge, and that's where this quote comes from, probably the world's first successful moving pictures. I found some pictures of this online. They weren't great, so I took that photo myself when I was walking to the conference reception there. Quite nice to be here. So I would make this claim that videos to study rheology, as with all moving pictures, can trace their history back to Leeds, England. So if anybody goes forward with proto-rheology videos, I really hope it's the folks that are hanging out locally here to celebrate that history. Okay, let's get back to thinking about the science. So most of the examples I showed you, most of them were viscosity yield stress examples. Nowhere did you pull out an elastic modulus, an extensional viscosity, etc. That it does exist, of course, when we think about that bouncing silly putting, and we think about the material functions associated with it. Questions come up like, this thing impacts, there's a certain time scale, what does that relate to? It relates to a frequency, as I'll mention soon. What about the bounce height? What does that really relate to? It relates to a tan delta, as I'll mention also. How about the time scale of the flow? This is actually a common misconception that I encounter when I'm instructing, is that oftentimes the time scale you see in the bottom row will be associated with a relaxation time. But it turns out the relaxation time of this material is like 0.1 seconds. It is very short. This is not a relaxation time. All you really see is the deformation in response to an applied stress. Maybe you see a retardation time if you haven't yet reached a steady state flow, but actually the retardation time is even slower, or faster I should say, shorter than the relaxation time. So all you're really seeing is the viscosity. The viscosity on the order of 10 to the 5 Pascal seconds, if you'd like a reference for it. Remember the tar pitch? It was like 10 to the 8th, 1,000 times more viscous than this. One of my favorite examples of elasticity comes from the late Jim Swan, who many of us remember. He was a professor at MIT. And one day on social media, he posted this beautiful video, which is him making a Japanese tonkotsu broth, where he observed the viscoelastic wave. And I have the video that Jim took for us. Isn't that beautiful? I love that. Yeah. So what would you ask someone to quantitatively extract from that? There's certainly a wave speed that we visually see. What I asked Jim was to give me a rough estimate of the complex modulus based on the wave speed, because I figured he might actually do it, and he did. He estimated it from the wave speed to be about 10 pascals, which is very, very soft, but actually believable considering this material. And he did that from a simple analysis that the wave speed always scales something like the square root of an elastic modulus over the local density. And the protorheology perspective would be just to rearrange that, to pull out the apparent G star based on what you're observing in terms of the wave speed. So with all of these fun examples, I hope they've been fun. Let me try to bring some organization to this. And one of the ways to organize is in terms of the 4 or sometimes 5 key phenomena of rheology. You've seen pictures up here before. If I go through the list, other things that are important, these are really inspired by McCosker and others before had thought about these ways of framing it, but Chris in his 1994 book really made it very clear based on these categories. That these are of all of the possible rheological phenomena, these are 4 extremely motivating phenomena, especially to motivate somebody sitting down to read a book. And they're up there. I want to acknowledge one thing. I haven't said anything about microstructure. If you're like a material physics sort of person, I'm sorry. I will at least acknowledge that, of course, many different microstructures give rise to these different phenomena. And I think in the protorheology perspective, you'll see us taking a bit of an agnostic perspective on this. Maybe you do want to know what the microstructure is to guess what's important, but we're really working at the continuum level. Let me show you some more videos from the key phenomena. So here is a bouncing putty and a time-lapse video. I think when Oliver mentioned that he uses some of my videos for teaching, these were the ones he was referring to. These are all to try to make it even easier than YouTube. YouTube is so bloated with advertisements and stuff if you don't pay for it. So we actually put these as supplemental video files to that annual review paper to just download them and use them directly. Here's the one you already saw. I'll skip past that. Here's a rod climbing one. Every time I do more broad outreach, this is the one that gets the gasps from people, of course, that they're not expecting this to happen, and then it's really hard to explain what's going on in an accessible way. And extensional thickening as well. I'll play the video here. I will confess, we have not actually tried to quantify these things in the videos, again, because a few years ago, I just stopped at the qualitative inference, and I never pushed to be quantitative. So maybe an invitation. Maybe one of you can write a paper analyzing one of these videos and just say what the protorheology inference is. And finally, there's a video on thixotropy. I'm not sure we have the time to wait for this. But I will show it because I guess I still continue to look for good examples of thixotropy videos that visually demonstrate thixotropy. Here we tipped it over. The little tilt test, only for a moment of time, shows that there's some high viscosity. We see that while it's flowing, you can see much more motion. This is, by the way, a special type of honey from New Zealand called Manuka honey that people recognize has this sort of property. When we pull away, you'll see that the viscosity remains low even though the shearing has stopped. And that's your visual evidence that for something called thixotropy. And this gets into an interesting path, but I'll just point out that some people like to define thixotropy in terms of the microstructure. Others prefer something more phenomenological. But if you see this video and you say that is thixotropy, you're definitely using a microstructure agnostic definition. It's what you see in terms of the flow that then in your mind you're probably connecting to a structure, of course. Anyway, that's an argument and discussion to be had later. So we're back to protorheology. So we saw this opportunity to really organize things. I'll show you some of those equations. We made a big list and created schematics for a whole range of things. This is incomplete, but was very instructive for us. You'll see some hits like the slump test. You'll see some hits like the falling ball viscometer, which seems simple. Of course, you can buy instruments that are based on this technique, but if you're just in the lab, you can do something very quickly as well. We mentioned the bubble being trapped. We talked about the tilt test. And we wanted to make sure we had at least representative examples that could touch every one of those key phenomena. That's what seemed to be missing. We weren't really sampling fully. Another acknowledgement of why this is difficult. It's difficult because there is no single universal constitutive equation like there is for Newtonian fluids. If I assume it's Newtonian, the inverse problems are very easy because I can assume I know the governing equations, apply them, and do parameter fitting. But it's more than just parameter fitting. Sometimes it's model selection and knowing what model is most credible to even describe things. I think that's part of the future opportunity in this space. But I will say that I think the time really is now. I think that the constitutive model understanding we have is developed enough that we really can do model selection and model comparison. We've done this in our group in simple ways. The fluid mechanics perspective is much harder because not only do you have to solve the forward problem, you have to solve it many, many times in parallel to compare and optimize. And so it's that computational cost that I think is the current bottleneck that we're working to get past. But I really think we can do it. So we organize things, having no single universal constitutive equation, we organize things based on the phenomena. So the first lumping together are examples of things that could give you viscosity or shear thinning if you're careful to look at two different stresses. What's important is to not just gather equations for viscosity, but every time you report a viscosity, you want to report out the characteristic loading under which you're observing it. You know, things are shear thinning, so tell me what stress or strain rate. Most of the time, for that forcing term, it's a stress because you're seeing something responding to gravitational forcing, maybe a pressure, almost always gravity in these particular examples. And so that's what we think we should be reporting is some characteristic stress. I won't go through these in detail. I'll give you one example, though, which is the viscous gravity current, solved in 1982 in JFM by Huppert. Beautiful forward problem. Now, it requires you to assume a Newtonian fluid. So depending on what you're looking at, you may or may not be comfortable with that assumption. If you're looking at this type of material, which is a schematic of a cat being poured into a bowl, take a moment to let that settle in. This is actually a nice comic that was sponsored by the Society of Rheology Venture Fund, inspired by Mark Fardine's article in 2014, that I think was a celebration of Gareth, if you look very carefully at that article. And the comic is cute because they show different rheological behaviors using little schematics of cats, like is a cat a liquid because it takes the shape of a bowl, etc. It's playful. But it's funny that in that comic, they show schematics that kind of map to the protorheology stuff that I'm talking about. So with the putties, you can do a time lapse of a gravity flow. Do you believe we can apply the Newtonian model? It really depends. Isn't this material very viscoelastic? How can I even assume it's steady state? So you have to be very careful. But I made the argument earlier that there's evidence to believe the relaxation time is very short, less than a second. You could do a torsion test quickly, and you'll feel that the stress relaxes quite quickly. I think torsion's the easiest. If you're ever doing this yourself or teaching it, the stress drops very quickly. And if you torque it and wait a second and let go, you don't see the elastic recovery, which is visually even more striking, I think, than needing to feel the torque. These are images taken over 10 minutes, much longer times than the relaxation time, and so I'm probably at a steady state flow under some characteristic stress loading. And when you do the analysis, you pull out that from the protorheology, I'm sorry, a transfer to the local PC means that Bill Gates came in and changed my approximately equal sign to a box. But the viscosities you pull out are different. They're both on the order of 10 to the 5 pascals, maybe a half order of magnitude lower. And actually, that's not that far off from what you would get with careful measurements. Here I'm showing linear viscoelastic measurements, where I represent these viscosities in terms of the G double prime you might expect to see at a frequency that corresponds to the time scale of this observation, which is 10 minutes. And of course, they're almost always going to be farther to the left than your patients to do the frequency sweep, because this will always take more time than it would to do a creep-like test to get this data. And that's where they land. So there's kind of a check that actually you can believe these things, but you have to be very careful, as I demonstrated, thinking about the assumptions built into the equations. I think I'll skip over those claims. I just made them. Let me go on. So let me talk about yield stress fluids. Maybe the most useful way to be rheologically complicated is to be a yield stress fluid, which really means, in my mind, that you have dramatic shear thinning and there's some characteristic stress at which that occurs. Maybe there's elasticity before that happens. That's important, or maybe that's not important to you. But it's not really a material function, of course. It's the forcing stress that we find. And so in the working equations, you don't see a viscosity or a modulus. What you see is the critical stress at which some nonlinearity sets on that's visually apparent. So this is a dramatic yielding. It's not the initial deviation from linearity, something that causes flow. And many of these are the things that we see a lot. I don't know if Philippe Cousseau is still here. I saw a great talk from Philippe, of course, the extensional gravity-driven dripping. Beautiful stuff, and it's very much in the space, although he does very clever analysis to even get the rate-dependent extensional stress, so he fills in a steady flow curve, a semi-steady flow curve. I'm more interested in the other phenomena, like the viscoelasticity. Jim Swan's viscoelastic waves is one thing, but there are other ways, like the bounce test. To get this, I want to talk about the bounce test for a moment and how you might use that. Also, we found an example in the Rheology of Cats comic where they showed a cat bouncing also. It's like every protorheology test, we find a cat example in that comic. So what you can get is the fractional height of recovery, and Rod Lakes, in his textbook from several years back, solved for what the loss is due to a half cycle of loading, assuming, for example, a damped oscillation that's damped, but you look at a half cycle. And so you end up getting this beautiful result that what you can actually see in terms of the fractional recovery is a ratio. It's related to a ratio of loss over storage. It's not exactly tan delta. Tan delta shows up tucked in the exponent of this function. So you have to rearrange this. And if you do it right, and you infer the tan delta from this, you get, let me switch to the pointer for a moment here. You get the protorheology here. Now, when I've seen people first do this, they report a tan delta and they plot it as a horizontal line, but it's not a horizontal line. There's a particular frequency associated with that impact time. And when you do that analysis, you pin it to nearly 1,000 radians per second. That's a very short impact time of a few milliseconds. And you see something funny. You're going to say, Randy, that doesn't match. This is garbage. Here's your cynicism. It should have entered earlier. Protorheology teaches me nothing. But I would say we still learned something. I mean, if I'm being really cheeky, I would say, well, you don't know that maybe this turns up all of a sudden. It probably doesn't, of course. But this introduces a good opportunity for me to say that for this particular tan delta, it's either a lower bound or an upper bound estimate, the way the analysis is. Which one should it be? We assume in this model that all the dissipation happens in the material, but it may not. You have dissipation not just from aerodynamic drag, but also the substrate, the adhesive contacts that are removing. So the real dissipation in the material is always going to be less than the total dissipation you're using. It means that this tan delta is always an upper bound estimate. And so really it's not an approximately equal. Maybe it's like less than or equal to, which means this is an upper bound and it should definitely be below. And it helps us rationalize that at high frequency, I can still believe this data. It's still consistent with this upper bound analysis. And it maybe gives me a way to visualize to people what tan delta means, at least at that particular frequency. Okay, another example. Gosh, and there was another cat example that Tanvir found when he was doing this too. Okay, is gravity-driven extension. So here's another one with the putty. So if I handed you the putty, we've done this at short courses a lot, and I asked you to estimate what you feel, maybe you'd say the viscosity. A quantitative estimate of shear viscosity you saw from the gravity settling. How about extensional viscosity? Oftentimes we'll grab it, we'll pull it, we feel some extensional viscosity. But just like Troughton, in 1906, I think it was, Gareth can correct me if I'm wrong, we can let gravity do the work for us, and it turns out that with very reasonable simplifying assumptions that turn out to be very good for this material. I'll do the test for us at the front of the lecture right now. So I'm going to grab this. I need some rough estimate of what this length is. It turns out that if, with the analysis, somebody start a timer for me. I'm 5 minutes before the top of the hour here, 5 seconds. As this thins, the stress is highest near the top where I'm gripping it. That's where it will thin the fastest. And if I just think about an analysis at that point in time, I can kind of neglect what's going on below, if I can neglect accelerations, which I'm now going to do. And if I follow that in time, I can derive an ordinary differential equation for some averaged extensional viscosity. That gives me an ODE for the dependence of the minimum diameter as a function of time. Now that's something, and I could try to fit this. It would be crazy to take a video. I mean, you could do it. Take a video, do the image tracking. You could definitely do that and fit the solution to the ODE. Turns out, though, you don't need to do that. If you just know the breakup time, you can use that to infer back to your averaged apparent extensional viscosity. I'm at about 50 seconds here. Wait till it drops. You'll see that the dynamics accelerate rapidly near the end. I think that we'll still be able to neglect inertial acceleration. You see the velocity rate of change is slow. But things happen so dramatically at the end that there's a very short amount of time between when it will close to hit the floor and when it would have broken up that we can neglect that. So I'm at 1 minute and 10 seconds right now. Still going. Do I want it to hit the floor? I'll let you see. There we go. Oh, it even bounced. You could get some tan delta from that also. So my time on that was maybe 1 minute, 25 seconds or so. Somebody could do this analysis for me right now. I tried to get it to be a distance that means that its characteristic stress is about 1,500 pascals. And it turns out that the equation is quite simple. I have it in the table here, that if you're willing to report an averaged extensional viscosity at the range of characteristic stresses, it's just the characteristic stress, which is this. You don't need to know the diameter, just that initial length, which is kind of nice, times the time to break. Of course, this will be wrong. but it'll be your first approximation to know where do you fit within the instruments that you have available to you to make the measurement. And maybe when a collaborator comes to you next time and they say, can you measure the extensional viscosity? Maybe you'll send me a photo of you doing this in your office to say, Randy, thanks, you told me how to tell my collaborator there's no way I'll be able to do what they would like me to do. We can compare quantitatively for this particular test shown here. This was the clock in my office right after we derived the equation. It was so exciting, we just stayed a little late and we did the test. And the data from Protorheology lands here. We plot it on a plot of compliance versus time, where that flow viscosity would be indicated by the dashed line. We locate that circle, though, at the longest time scale of our observation to try to give some sense of where we were along that curve. And we also have to be careful to report the forcing stress. With the linear viscoelastic data, we took that at 30 pascals, but this data was not 30 pascals, it was larger. It was 580 pascals, and so it helps you to check in, was I going a little nonlinear, and maybe that's why I have more fluidity, or maybe it's just an uncertainty in something else. Actually, it turns out this is pretty still in the linear regime. You need to go above several thousands to be in the nonlinear regime, at least with that pink putty there. Okay. I could go on with so many other examples to you. The goal being to give you a sense of how you might benefit from doing this or not, and you just leave the conference and brush this aside. That's fine. But I do want to show, but this next case study has another lesson that we learned, which is related to when you try to infer something, you need to be careful to associate it with the conditions at which you're inferring it. So we all know for a while we have good estimate equations to infer from dye swell experiments, like the polymer liquid coming out of the syringe. To infer back to a first normal stress difference, you have to assume a model, something like Oldroyd B or in that class to make this connection. And we get these results. We can compare that, and this has been done, this is not necessarily new, to get out a normal stress difference from the dye swell. And actually in this case, and one reason why it's nice, is you can extend the range of your rheometry because we would see edge fracture in this particular case before getting up to this point. That was nice, but what was more interesting is that we tried to infer something about a relaxation time because I wanted to use this visual, not as evidence of a normal stress difference, but more specifically viscoelastic stresses, specifically elastic stresses that then relax to make the deformation recoil to make that expand out. And so the expressions that relate to inferring a time scale also require a model assumption. So there's your continual asterisk to keep checking back in on. But you can get it. And when we first calculated that time scale, it was really short. It was like 30 milliseconds. Hard to measure that in a rheometer. But on the rheometer in the linear regime, it looked like it was about 0.5 seconds. Very different. Is this inconsistent? No, it's just at very different conditions. Of course, to see dye swell, you need to be at a very high Weisenberg number. So the time scale that we're trying to infer is also associated with a very high Weisenberg number. And so we tried to map to that by doing frequency sweeps at different amplitudes to try to see there are many ways to pull off a characteristic time. We looked at the crossovers. And we plot that characteristic time here as a function of the Weisenberg number, and the first two open points are from the frequency sweeps. And here's where protorheology would land if you acknowledge that you're measuring that time scale at a particular Weisenberg number. So again, it seems crazy low, but it's not inconsistent with what the trends we see when we look at amplitude-dependent time scales. This has been particularly inspiring to see timescales because we're getting into projects where we're working with mutating systems where those the viscoelastic timescales are changing while we're doing 3D printing. And so we're starting to explore using this as a way to check in on that mutating material. The biggest lesson learned, though, from this is that the property you report out should be associated with at least two things, the forcing strength and the timescale. That's come up a lot here. If you're familiar with Pipkin maps, think Pipkin map in this way. There's some characteristic Deborah number and Weisenberg number, or some transient time scale and some forcing strength. The forcing strength, I think, can be at least one of three things. It's either a stress or a strain rate or a strain, depending on what you're doing. That's what I mean by forcing condition. Maybe you're looking at a solid. So, more case studies, but in light of time, I'm going to be selective in what case studies I point out. I want to show you case studies that are actually in the published literature to point to where something like protorheology has helped to enhance the result. So I'll skip this first one here, and I'll jump to this one. This is from Yilin Wang, who's a recent PhD student from our group at Illinois, and she was thinking very carefully about trying to think what is the difference between thixotropy, anti-thixotropy, and viscoelasticity. I gave her a challenge: give me pictures that contrast the three materials you're looking at, that relate somehow to those things. It was really difficult, if not impossible, to get some visual associated with anti-thixotropy. So that's an invitation to you all to show me how I can see anti-thixotropy. It's because it's subtle. You can see it on the rheometer, very high signal to noise, very delicate. What she was able to show, though, is that these first two materials definitely have a yield stress, and she could quantitatively look at the pictures. That was consistent with the data, but it was nice to be sure. We didn't have slip, for example. We didn't have such dramatic thixotropy that after working the material, the yield stress dropped. And used the dye swell to point out that that sample had significant elasticity by that particular measure. There are other flavors of using this. Here's one that was a collaboration with Chris Evans and his group. The student who was leading this was Ellie Porath, who's now a postdoc at ETH, working with Jan Vermont. And this was fun. So this was with a Vitrumer's project. And with Vitrumer's, I always run into this confusing thing of people wanting to call them solids, but they flow at long times. And as we rheologists know, you know, if it's a solid or not is all a function of a time scale. But I've always wanted people to show me the evidence that this material is really a solid over the time scale they're claiming, or it's really a fluid over some time scale. And so we pushed our collaborators this way. And so I got Ellie to do some time-lapse photos of the spheres flowing out, helping to rationalize this really is a fluid rather than a solid over these time scales. We did that same type of plotting of the apparent G double prime at a lower frequency than we happened to catch with the frequency sweep. And then we did the bounce test, which also helped us rationalize some important things. You see in the upper left here, this is a schematic plot of the relaxation spectrum, and one of the cool things of this paper was to show that we thought that there were two distinct dominant relaxation times that we could distinguish in the relaxation spectrum, which should mean that we have extra dissipation at higher frequencies, that the protorheology was able to pick up a little bit. You see that as this is trending up, we kind of confirm that it should keep trending up in this way, helping to give a little bit of corroborating evidence to our spectrum interpretation. More recently, it's been fun to interact with chemists, especially. I think we must have chemists in the room, but with all the chemists I collaborate with, they're always telling me everyone seems to want the tilt test, and I tell them, don't do it. Don't do the tilt tests. You know, is it really a solid or a liquid? You don't know how to interpret it. Surface tension screws things up, et cetera. And I appreciate that. So we were very cautious in this following publication here that just appeared, led by Jacob Lessard, where he decided to barrel forward anyway and use the tilt test as a way to estimate an important thing for down selecting a huge range of formulation chemistries for additive manufacturing, where these are mutating samples and they have a finite pot life, where cross-linking is occurring in the background, and at some point the viscosity is so large you just can't work with them. And so he surmised that maybe the tilt test would be a surrogate metric to identify that point, which he could do much faster, and he could do in an oven at the right temperatures. And he did it, and he even compared with rotational rheometry. In red is his inference of the resin lifetime based on the tilt tests, which is when he flips it and he waits 10 seconds, he can't see visible motion, which seems kind of silly. We can back out a viscosity inference from that, but he wasn't doing that. It turned out that landed exactly on the time scale at which he saw at a particular frequency of 1 hertz, the G prime, G double prime crossover. I think there's a lot of luck in that, in coincidence. That is not a general truth, but it happened to be very good for this class of systems he was looking at, and I think Jacob is now becoming an evangelist of the tilt test for high throughput testing, and we'll try to rein him in to make sure that we keep all of the caveats in mind. Here's another, I want to give this example to you also because I think that many of us have collaborations that come up this way. A collaborator comes, there's some aspect of their work that involves rheology. They want someone with that domain expertise to help them improve that part of the paper. For me, these collaborators almost always are taking pictures. We've got the tilted vial test here of this particular gel sample. They squeeze it out of a syringe and they wrote UIUC for University of Illinois Urbana-Champaign. They're doing self-healing. They're doing this is like their figure 3 is all full of protorheology. And they said basically nothing about it because they weren't sure where to start. You know, what am I really seeing is the question that all of us in this room have the skills to help people answer. What is it I really see? For example, in the tilt test, what you really see is a viscosity, but you must report the time scale of observation. I can put this silly putty in a vial and tilt it and pretend like it's a solid if I bring it back 10 seconds later, and we know that it's not. Really, the viscosity is just very large. And that's what you can really infer. I can't tell you anything about the modulus. I can just give you a lower bound estimate on the viscosity, which we were able to do from these quick tests. This other one with the syringe, this was nice because we weren't able to collect good shear rheometry data because we had edge fracture. Well, we wanted to demonstrate that it was shear thinning in a practical sense. They pushed it through the syringe, we pushed it through the syringe, and we did some very quick analysis just to get some qualitative evidence that this really is shear thinning to help some reviewers believe that this really could be processed. Maybe you'll find yourselves in similar situations. I know you found yourself in the following situation, which is that you're at a conference where the BSR is handing out little tins of putties. I don't know, does anyone happen to have their handout from the BSR right now? Mine doesn't have the sticker on it because Richard sent this to me back in February, so I could take a sneak peek at what's going on here. But you have these tins, and there's kind of a sandy sample, I think that one called the fluff. What are the names we have for these? And the other's like a bouncing putty. So this was fun and very contemporaneous. So let's finish with some fun here. So when I got these, the first thing I did was I put them on my desk and I did the time lapse. You know, well, the first thing I did was I lifted them out and I squeezed them, and I could certainly deform them. They would hold their shape. They held their shape for over 8 hours. There's the same clock you saw before I took it off my wall to co-locate it with the samples here. So maybe I could give you a lower bound estimate on the viscosity of these particular stresses, and I think you'll observe the same thing. These things look very solid-like in terms of not showing significant flow under these stresses. More interesting, I think, was to do bounce testing, and I think the blue thing even is called bouncing putty or something. And you see a bounce, and then it falls into my lap, and I have to chase after it. The yellow one doesn't bounce at all. I'll show you the video, slow-mo with my pocket computer. Boom, nothing. So it's the same materials here. I'll drop the yellow putty now in 3, 2, 1. Same thing. Let me drop the blue putty. I called it a putty. It's really a foam. I don't know what it is. It's a sand suspension. I'll drop the blue, 3, 2, 1. And that bounced a little less than what the video was. It's because I think it's dried out and it has a skin on the outside. But that's when it was fresh, and I think that's representative of what you see in the tins. And let's try to do some analysis, which I tried to do last night after getting some data also. What I see here is a fractional height of recovery of about 1/3. Using the equations up here, I get a tan delta. That's my upper bound estimate of about 0.15. I connect it to some very rough estimate of time scale. I actually don't know what the impact time is. I didn't get that high speed of a video. But I can reasonably estimate the stress, although that also depends on the impact time, so there's uncertainty here too. But just in round numbers, 6,000 pascals is a lot and is probably certainly above the yield stress that we observe here when I drop this. That stress is around the same, I think. Here, what can we say when this thing is like a sandbag and does nothing? You could just move on, but actually, it turns out that if it doesn't bounce, it doesn't tell you that tan delta is diverging to infinity. So all you can say is that tan delta is greater than 1. And you don't know how much greater than 1 it is, the way that the analysis works out. Because as soon as it gets 1 or above, the way the function is, you just can't notice any recovery. Again, at the associated frequency and time scale. So this was data taken here at the conference by Tree, which is pretty cool. That confirms not unreasonably that there is dissipation. I'm sorry, this isn't super clear. This is G prime, pretty horizontal, doesn't really relax. That corresponds to me not being able to see any flow. The relaxation times are much lower. And the tan delta is around 0.1-ish or so. You can look a little more carefully there and see it's actually a little bit above 0.1. I haven't quantitatively looked to see how close it is to 0.15 if the upper bound estimate really works. But probably the upper bound estimate is at a stress that's much larger than what was used for this test, and we haven't compared that yet. Richard also did some of his own experiments. He tried to measure the yield stress, which was a lot of fun. That was a little harder. He came up with this device with a syringe and kind of a manometer-style tube. It made an estimate of the yield stress. What I loved about the photo he sent was that he wrote it on a Post-it note. That's the spirit here, right? Make it quick, make it reasonable. This seems a little silly, but these materials are actually really hard to test, and Richard kindly went around asking some of the instrument manufacturer exhibitors to try to test the material, and you know what? I didn't get any data from it because it suffers from problems like slip. As you see here, the top geometry is just spinning on top of the blue. And in oscillations with the yellow, you also see slip. I love having the videos. It tells me I can't trust the rheometry data I'm going to get. So if nothing else, please post your SI videos with your papers, convincing me and everybody else that we can really trust your data. In light of time, I'm going to say that, I'm going to jump ahead. Been doing a lot of high throughput testing. The one thing I want to land on, though, is that I'm a proponent of avoiding bad data, and I hope you are too. One way we've done that with other rheometry is to think about operational limit lines, and Oliver kindly mentioned the publication award is one of those places. There's a book chapter I tried to pull together on this also, to do things like you see on the right, which is even before you measure the data, you can already plot these dashed lines that give you some estimate of where you can believe things and where you can't. We don't have any of that for protorheology yet, but I think there's a path forward. The trick is that you take criteria that relate to things like the Reynolds number to neglect inertia, minimum measurable things, viscoelastic wave speeds, like you saw, instrument inertia, and the trick is to somehow rewrite those in terms of the viscoelastic or viscous material functions that you want to plot, Rewrite Reynolds number in terms of a viscosity and a shear rate, and you can get the upper right dashed line over here. We need to do that for protorheology, and it's not obvious, but I think it can be done. This is recent work from Ramdas Tiwari, where for the tilted vial, there are a few key limits. I want gravity to drive the flow, not surface tension. That gives me a Bond number limit. I want viscosity to resist that driving force, not inertia. It gives me a Reynolds number limit. I need to be patient enough that when I flip the vial, I can actually see something. This gives me an upper bound limit on my viscosity, it turns out. I can only test certain vial sizes. From Thermo Fisher, I can buy small vials and big vials. Maybe if I wanted, I could do it in this, but you're limited based on vial size. And if you pull all of that together, you get the following operational window. Not of viscosity as a function of strain rate, because we're not controlling strain rate. We only control something of the gravitational forcing. So the clever trick is to think viscosity versus stress, and then this emerges. And this is what we have, which I find really interesting. The ranges of viscosity we expect to see in vials is something like 0.3 to maybe 10 to the 4 Pascal seconds, or longer if you're willing to wait for it. But if you've ever taught by putting viscosity in different vials and handing them out to students and having them flip them to see if they can tell, you might have observed that it's hard to tell the difference between water viscosity and olive oil viscosity, and I think this is one way to understand why. It's outside of the operational window. The viscosity is so low that inertia resists that gravity rather than viscosity resisting. And to give you another quote before closing, Rob Poole confessed to me that he does this very thing with his students, gave students vials of viscous liquids, asked them to guess by what factor is the viscosity greater than water. They weren't very good at that. I hope we can find ways to make them better and all of us better at doing these sort of things. So in conclusion, what you've seen is that this idea of protorheology is not new in a sense, but I hope you've seen more of a gathering of the ideas to find patterns and best practices for this. I hope you've seen a test you haven't thought of before. I hope you've seen equations you haven't come upon before. We had to derive some new ones in that paper. And going forward, I think there's a big invitation to those of us that do fluid mechanics, solid mechanics, inverse problems, as I mentioned near the beginning, especially things like my favorite way to do model selection, thinking in terms of Bayes' theory of probability. As a final thing, though, I'll say that it's not just the journals, Journal of Rheology, Rheologica Acta, JAM-NFM, Soft Matter that should be doing this. Even Nature Materials recognizes the value in showing pictures. And there was very recently, the day after the protorheology paper was published, was an editorial in Nature Materials titled Trust But Verify that describes the value of verifying the data that we have out there. And this is a fun thing to read through. It's very short, a couple collections of papers. So we find ourselves in Leeds, the birthplace of moving pictures, and Leeds AERC 2024 is your invitation for more protorheology. And I'll just leave this up. Thank you for continuing to be here and your time, and a great week at the conference.
I realize people may have to leave, but I'm sure people might have some questions for Randy. Let's a hand up.
I see some, but I'll let you dictate because I know the timing might be tight. And I'll be around afterwards also if people want to connect.
Great talk, Randy.
Thank you, Yogesh.
Isn't the limitation of protorheology is people's ability to judge length scales and time scales?
That is one of the limitations, is our ability to judge length and timescales. Whether it's just a rough estimate or computer imaging, even with computer imaging, this will be some limitation.
When you go to computer imaging and, of course, having the frame rate, and then of course, you're going into more quantitative.